Okay, so I'm going to give an introduction to the European Environment for Scientific Software Installations. That name, of course, is gamed a little bit to give us the acronym EESSI. That's what we call the thing, right? So it's called EESSI. It's an initiative that comes really from, so I'm a maintainer in EasyBuild. It's an initiative that's connected to the EasyBuild community. Most of the initiative is coming from that EasyBuild community. And so Kenneth is like the benevolent dictator for life of the EasyBuild community. He always really likes to use this cartoon, right, to explain like what EasyBuild was trying to do in terms of like helping people to install software. But they were so busy doing that they didn't have time to see that perhaps there was a better way, right, that could actually help them out to do that job. And I feel that probably with EESSI, it's also something similar, right? People are so busy with what they already have that they can't see that it's hard for them to see that there's perhaps another way that could be more efficient for them. So my name is Alan Akash. I'm currently at the University of Barcelona. I spent about, I think it was nearly 11 years in the end at the Jülich Supercomputing Center. I also connected to CECAM, so that's like it's an atomic and molecular physics organization. It's one of the oldest organizations in Europe in the scientific space. It's more than 50 years old, yeah. More than 50 years old. So it's a network of scientists across Europe. So I'm also connected to them as well. So, talking about EESSI in particular, right? So what's EESSI in a nutshell? So we have that acronym, that gamed acronym, EESSI. And right now it says European in that acronym. And that's for good reason too, because we needed to get European money. So that was a good way of doing it. Probably in the end, there's not really anything that restricts us to being European, right? But that's the way it is right now. In the end, we might change that acronym to be a self-referencing acronym, so it will become EESSI Environment for Scientific Software Installations. That's probably what we'll do in the end. It's a shared repository of optimized software installations, right? That's the difference. You don't build anything. You as an end user won't build anything. The installations are shared. So whether you're on a resource, whether it's your own laptop, in a VM on my own laptop, for example, that's where I typically use it. On a server, in the cloud, on an HPC system, it's the same software stack everywhere, but optimized for the hardware that you have available to you in that place. It's uniform, so because it's the same stack, it's uniform. So the way you use that stack is the same regardless of what resource you have access to. And it should work right now on any Linux OS. It also works on WSL, so on Windows as well. It could work on Mac OS, but there's just a couple of hiccups that we have to get around on Mac OS. So we do everything right down to libc, and you can't do libc on Mac OS, so we have to figure out how we're going to get around that. But right now, as of now, it works on any Linux OS and also on WSL, so on Windows as well. It works for all those resources, from laptops to workstations to HPC clusters. It works for lots of different hardware. So it works on Power, works for ARM, works for lots of different Intel or x86 CPUs as well. And it supports all those different CPUs, lots of different interconnects as well, basically anything that's out there. GPU support is in a pull request right now, so we're on the verge of having GPU support in there as well. Our focus these days is obviously on the performance of the software that we provide, how we include that software, so automating the process for contributing software to our shared software stack, testing what is inside our shared software stack, and in general collaborating around that whole process, right? So how do we include software? How do we collaborate among each other to make that as easy as possible and get this workflow nice and smooth? We have a website. The website doesn't have much. It probably hasn't been updated in forever. The documentation is pretty good, though, and also includes details about how you can try out our pilot setup. So I'd recommend if you want to learn a lot more, you can go to our documentation about that. So when I talk about scientific software installations, and here we're in the HPC space, so we care about how fast they run, right? So we had this discussion a little bit already today, but we really care about the fact that they are optimized scientific software stacks. So it should be software we use should be optimized for the system where we want it to run. And the impact on performance in that respect is pretty significant, or can be very significant, especially when we talk about scientific software. So this example is a little bit old now, right? But going back a couple of years, and we looked at what the difference is when you compile a typical scientific application, or maybe not so typical, the GROMACS in this case, and a benchmark that came out of PRACE. So PRACE is a big pan-European HPC organization, and they had a special benchmark case. So we ran that benchmark case on the same system, but using different optimizations of the stack. So basically using different instruction sets that were available. And the system was a Cascade Lake, so you could go all the way up to AVX 512. We looked at the performance, right? So basically, the performance from GROMACS, at the end of the day, at the end of a simulation, it prints out how many nanoseconds per day you could simulate. And the more nanoseconds you could simulate, the better the result. So from a YUM installation of GROMACS, you got 1.09 nanoseconds per day on that system. And then we had inside EESSI, we have all these different versions of that executable available, so for the different instruction sets. So we ran them all. And we went from 1.02 nanoseconds per day on a generic, so just SSE2, all the way up to 1.85 when we use AVX 512. Now, GROMACS might be a special case a little bit because it is optimized, right? People spend a lot of effort making sure that GROMACS is optimized. So this might be a bit of an outlier in terms of the amount, but the fact is, the speed up was 70% just from using a different executable. So the loss that you have when you don't use an executable can be quite significant, right? So this is an important thing to consider, right? When you think about things like mobility of compute, for example, where you move an executable around from different places. It may work, but that doesn't mean it's optimized, and you might be wasting a lot of CPU cycles because you don't use optimized software. So what are the goals of EESSI in general? So, well, the major goal is we want to avoid a lot of duplicate work. So that was one of the reasons that the EasyBuild project in general was started, to try and collaborate together so that everyone is not running into the same issues with software all the time, but that when we come to some kind of solution when it comes to software, that we share that solution with other people. And we have tools now that automate that software installation process. So EasyBuild is one of those tools. One of the other commonly used tools in that space is SPAC, also very, very, very heavily utilized. But they're not really enough, because those recipes, that whether we provide them through EasyBuild or SPAC provides them, they do break on occasions, right? And they sometimes don't work. And so it's no guarantee, just because a piece of software appears in EasyBuild or in SPAC, that it will work on the system that you have access to. That may not be the case. And if you're not an expert in EasyBuild or SPAC, resolving that issue that arises can be a very, very difficult thing to do. So we want to go beyond sharing build recipes and actually work towards sharing the actual installations themselves, right? An actual shared software stack. And we want that stack to be uniform as well. So we want to have the same software environment no matter where we are doing our computations. And we don't want to sacrifice performance, right? So we don't want to, just to be mobile, we don't want to have to sacrifice performance. And you do sacrifice performance when it comes to things like containers or Conda. Not necessarily, but typically, right? So you can have lots of different containers for different CPUs and things like that, but most people don't do that. Most people do it for the one that they have access to, and that's the one they use. And if they need something portable, something that can be moved around, well, then they drop the optimizations that they have to make that possible, so they can do it in a single image. And the other thing that it facilitates is something like HPC training. So in the past, what I've seen is that a lot of sites can have a small cluster that they use for training purposes. But that has to be maintained independently of the production system. And in many cases, that means that you have an outdated software stack on that system. One that is not reproducible on the production system, is outdated and slow, may not slow, and sometimes it doesn't work, it depends. But it's an additional effort to maintain that software stack on that training system. With something like EESSI, that's no longer an issue because you have the same stack in both places by default. And then the other thing one of those other things that we wanted to help is the development of scientific software in general. So if we can provide a solution like this, then other people can build on top of it. They can rely on it regardless of what operating system they have, they can rely on it to provide their dependencies, and then they can just do the added value that they bring to that stack, right? So which it might be their own application. So to give you a high-level overview of what the EESSI project looks like, on the very bottom we have the host operating system, right? So that's where we're getting our kernel. So that might be Linux. In the future, Mac OS or the Windows subsystem for Linux, but that's basically the kernel. That's what we're getting from there. And then on top of that, then you will have things like the Slurm resource manager. You will have your network drivers, your GPU drivers. We're not trying to replace those. We're going to use them, those that come from the host system. And so all the hardware that's supported by the OS that's on the host system, we will use that hardware that's available to us. So on top of this, then we have our distribution layer, our file system layer, right? So we heard about these Fuse distributed file systems already today, so this Fusion example. So we will use, we use a system like that comes from CERN, so it's called CERN VMFS, and we use that to distribute our software stack. On top of that file system layer, we have what we call our compatibility layer. This is basically, you could think of it like a container without a container runtime. So all we're doing is putting, in the file system, we're putting an operating system on top of the operating system that exists on the system. And we don't need a runtime to do that, right? We're just doing it in the file layer, in the file system layer. So we have a compatibility there, and because we then control this kind of like a container OS, because we control this operating system, it levels the ground across all the different client OSs that might be out there, so all these different Linux OSs. Now, up to this point, we haven't cared about the optimization, right? So for the compatibility layer, we do it on the basis of the CPU families, because we don't really care about the optimization inside the compatibility layer. When it comes to the actual scientific applications that we expect people to run, that's where we start caring about these things, and that's where we have the optimized applications and all the dependencies of those optimized applications. Now, the tools that we use inside here are ArcSpec, which is the thing that detects the architecture that we want. EasyBuild is what we do to actually build the software, what we use to build the software, and then LMod is how we provide a user interface to what we've done. On the left-hand side over here is the testing framework that we have. So we also use Reframe. At least ultimately, we plan to have a testing suite, a test suite for all the different software packages, particularly for the big applications, right? For the marquee applications, we want to make sure not only is the stuff working, but that it's performing as well and that it's scalable, right? So we have a whole testing framework to allow us to ensure that. As I said before, right now, we work on lots of different Intel CPUs. We work on a number of different AMD CPUs. We have also support for, I think it's three different ARM CPUs, as well as generic in all those cases. Power 9, we're probably dropping support for Power 9. We've kept it up for a couple of years, but to our knowledge, nobody's using it, and the Power 9 chips are going away, so we probably will drop that. We can bring it back if there's a use case for that. We've also done some initial work for RISC-V. So we've installed CERN VMFS and RISC-V. We built the compatibility layer on top of RISC-V, but it's kind of future work for us to work a little bit more on RISC-V. So, I'm missing a page here, but so I want to jump straight into a demo. So the demo scenario in this case is that I'm going to start up an empty VM, completely empty VM, in AWS, and I'm going to choose it to be a bit exotic. I'm going to choose an ARM VM, and I'm going to choose an exotic operating system, so Amazon Linux 2023. I never used Amazon Linux 2023 until yesterday, so it's an interesting example for me, even alone. So the VM is completely empty. There's no CERN VMFS. EESSI is not available, and I'm going to show how quickly you can make EESSI available on that system. I will have admin rights in here because I need to install some packages, and I'm going to need sudo to do that, so I will be a root user in here, or I will have sudo rights. And then we're going to set up the EESSI environment, and we're going to run some scripts from a particular location. So this is, well, we'll get to here in a minute, but basically we have some demos that you can run, which includes some scripting to actually install EESSI as well. So you can try these out, but basically it's on GitHub, it's under the EESSI organization, EESSI, and then it's EESSI again, //demo, or not //demo. So let's do it. So let me see. No. They're the wrong way around, that's why. Okay, so I can't see things now because of now. I'm going to launch an instance. And I want the Amazon Linux, the latest one that they have. So I'll just search for that. 2023, I want an ARM. I want the ARM version. I'm going to get something smaller than or larger than the minimum, because I want a couple, because I'm going to run a few examples, and they take a little bit of time, not a crazy amount, but I want, I'm going to get 8 CPUs here, and it gives me a good bit of memory as well. And then I need to provide a key so I can SSH into it. And that's it. So I launch an instance. Okay, now that's starting to come up. I want to connect to that instance. I'm going to use an SSH client to do that. So, yeah, I don't know how familiar you all are with the AWS interface, but basically it gives me the SSH command that I'll need to use to connect here. You won't be connecting here. This part is just a demo. But then I'm going to go to my cluster environment, so this prepared environment that we have. I'm going to use the same environment that you are. When you log into that environment, so I don't know if you have already. Oh yeah. So before I go on, because I'm about to start a job here, anyone who's created an account, has that been approved for you yet? So have people created accounts, and and this URL as well? Have you been able to log on to find this URL? Oh. It doesn't work. HPC. What's the host name you're using? Oh, sorry, it shouldn't be. I should have updated the slide. I must have made a mistake, did I? Let's see. No, it's right on the slide. Oh, no, sorry. It should be this. HPC KP. Sorry. So try again. Sorry about that. Yeah, that works. So if everyone goes in the web browser, the cluster will be full, but that's fine. Where was I? Here, right? These got moved around. So, oops. Okay, so let me go back here. Okay, so I'm going to start my server. So when you do this, you'll be presented with the same thing. I've already changed my time to 2 hours. I've already changed my cores to 2 cores, and I've taken 2 gigs of memory per core. There's no GPUs on the system, so that's not an option right now, and I'm going to use a Jupyter Lab interface. So in I go. All right, so now this is running a job on the system, so I'm running in the context of a job on the system. Oh, this is too large now, because let me. Is that still legible? That size? Is that okay? Bit bigger? What, is that okay? More? Okay. So some of the text will now start to float off the screen very, very quickly, but okay. Right, so in this environment, EESSI is already available. We'll get to that in a minute, right? But what I'm going to do right now is do SSH to this virtual machine that I created on AWS, right? So I already have my key on the system, so it already knows who I am. So you can see I'm on Amazon Linux 2023. There's nothing available, right? Not even Git is available on the system, right? So I have to install that. Okay. So now I have Git available, so now I can clone that repository. So this is the demo repository. I'm going to go here and get the Git URL. So if you have the URL, then it's just add .git on the end of it, and then go back to. I'm going to close those in a minute. Go back here and then git clone that repository. Okay, and then we can go inside. Right, we have a couple of, in this directory, we've a couple of examples that we're going to run. So we have one for bioconductor, one for GROMACS, and one for OpenFOAM, and for TensorFlow as well. But I actually don't have EESSI available yet, so I have no module command or anything like that. Nothing available yet. I go into the scripts directory. So there's already support for RHEL-based OSs and Ubuntu as well. There's also information here about how to start Singularity environments. We're on Amazon Linux, so I added support for Amazon Linux yesterday. We can take a look at the Ubuntu one just for hopefully it doesn't go off screen. Well, let's do less just in case. Just to see what commands are actually inside these scripts. So you can see we're just doing we're getting a particular package, which is the repository for CVMFS. We install that repository and then update the repository is available, and then we just tell it to install CVMFS. So these instructions come from CVMFS itself. We're just reproducing them here. But what we do have in ECU is we do have our own configuration file for CVMFS, which you need to install. So you can download that package and then use the same installation method. Then you make a small configuration file for CVMFS that we're going to use right now, and then you tell it to set itself up, right? The Amazon one looks a little bit different. So I did this yesterday. It looks different because there is no repository that works right now for Amazon Linux. So you have to go find the packages directly, right? So that's the general configuration for CVMFS. You have to install that RPM first, and then you have to install CVMFS itself, the RPM for CVMFS. And then you install the EC configuration package as well. So 3 different packages, you install those, you create the basic configuration file and set up the environment, and things should just work. Let's find out if that's the case. So we can run this through Bash, or we can run it directly even. 210, so this is the Amazon Linux one. So now lots of things will happen. It's installing all these packages, it takes a few seconds. Okay, right, so now CVMFS is installed. So we now have in this new directory, /CVMFS, but it's empty, there's nothing inside. So the reason that's the case is because we're using this AutoFS feature, so basically it's automatically mounting a location once you try and access it. So we can do an ls again, but I know that my repository, the URL for my repository is pilot EESSI -hvc.org, right? So if I do an ls in this location, something happens, and all of a sudden I have directories in that location. So if I go back and look at LF, we see we have 2 different things now. We've got the configuration file for CERN, a directory there, and also this new repository, right? The next step to actually make EC available then is to, inside this new location, this pilot EC location, you can take the latest version of the pilot, and there's an initialization script for Bash right now. We only support Bash at the moment, right? That might change in the future, but. Okay, and now it says, looking at what's available, I see it knows about some future architectures that are not supported at the time, so I also have support for Graviton 3 and Ultra, but it says, oh yeah, you've got Graviton 2, that's the directory that I want to use, so it uses a particular location underneath this new repository and adds that to my module path. And then it sets up LMOD as well, so our modules configuration also sets that up for us. And now, if we try and look around and see what's available, so say we want to use GROMACS, OpenFOAM, TensorFlow, for example, we can see all these things are available and in different versions as well, right? So we've got OpenFOAM, GROMACS, TensorFlow, and Horovod as well, if that tickles your fancy. So the screen, the text is a little bit too big for the screen here. It's a bit too small, not 80 characters, unfortunately. But anyway, the software is available. So now at this point, we're in the scripts directory. So let's go back and try and run an example, right? So let's go into, for example, we'll run GROMACS first. So in here, there's a run script. Let's take a look inside. So basically, it's loading a particular module. Let me highlight it here. It's loading a particular module first, and then if it needs to, it downloads the test case data that it needs to run this particular example, and then down the end is the actual GROMACS command, which is running something, right? So So let's run it. So we'll run that test script, which will download this data, and then run GrowMax command. Right, so there's the data being downloaded, and already we're running, right? So all of a sudden, we never installed anything, but GrowMax is now running on the system that had nothing when we logged in a couple of minutes ago. Oh, fatal error. That's not. Don't know why. Did I 32 MPI? Don't know why. This worked yesterday. Anyway, the executable is running. I'm not sure why it didn't execute correctly. I may have allocated the wrong system. I'm not sure. Let's try another example. That's the downside of doing things live. Let's try TensorFlow. So we've got another TensorFlow example in here. The difficulty or the complication with something like TensorFlow, it's a Python application. At runtime, basically, when I run an executable, what it's doing is, at runtime, it's pulling in the files that it needs to use to run that application. And for something like a Python executable, that's many files, right, that it needs to pull in. So it can be a little bit slower to start, but then once things are running, once it runs once, so this example should only take a few seconds, but it will take a little bit of time to start up the first time. But then it will have cached all those files locally. So when I try and run it the second time, the cache will kick in and it will run straight away. Yeah, okay. So this example is a bit better. Yeah, the width of the screen is a bit annoying, but okay. So there, we ran a TensorFlow example, right? So we had nothing on the system. Now we just ran a TensorFlow example. We can run the same. That took 20 seconds. Let's run the same example again this time. See if we get much improvement. It seems to start a little bit faster. So the second time we run, anything we needed to run that executable have been cached locally. So instead of 20 seconds, it takes 10 to run the same example. Okay, and then we could do the same for.
Sorry, where is this?
Where is what?
This folder with all these, with GrowMax, with with TensorFlow, because I can find it.
It's a Git repository.
No, yeah, but it's supposed to be in the machine that we just connected.
No, you clone it. You git clone, and you clone the repository.
We had to clone the repository.
Yeah.
Okay. I thought it was already here.
So that's the URL. So it's the easy organization /easy-demo, and then just add the Git. So there are people here. So if you have a question, there's helpers around. So if you need to do something, but you don't need to run this now. This part was supposed to be a demo. So we have like time for you to run this in a few minutes. Okay. So let me go back here. So the other example that came up today was OpenFOAM. So let's go into the OpenFOAM folder. We actually have the same example, right? So the OpenFOAM example is a little bit more, it's a bit more complicated. You have to run lots of different things, but it's the same example that was used before today, the motorbike example. So we're going to run that as well. So this is the OpenFOAM example. It's already running, right? So almost instantaneously, we have all these different software packages. It feels like very instantaneous, right? Like they're right there straight away. But they're not. They're being pulled down, right, as the files are being used. All right, so unfortunately, because of my screen size here, everything is going off the screen. Maybe if I kind of reduce it a little bit, just so 80 characters fit. So it looks a bit cleaner if I do it like this, right? So, and this will keep going, unfortunately, because it goes up for 250 time steps. So I'm not sure what happened to the GrowMax example. Probably if I looked into it, I'd figure it out. But you can see that the other cases also worked. There's another example. That's bioconductor. It will go to completion, right? It goes to 500 steps. I'm not going to let it go all the way. The other example was bioconductor. Again, another case where there's an awful lot of files. Bioconductor. So let's do less. So in the bioconductor example, well, there's not much here, right? There's a script in here called dna.r, and it's just running that script, right, which is using bioconductor. So we can run that example as well. And that's it. It's already running. I think this one is pretty fast. I think it takes about 10 or 15 seconds or something like that. Yeah?
If I understood well, the models that you cloned that appeared because so these have been compiled in a system similar to the one that you are, or really the same, or how do you?
Similar, right? So we're looking at the CPU, right? So because we have this our own operating system effectively on top of the host operating system. So that one's finished. That's the bioconductor example finished, right? So because we have our own host operating system, we're compiling based on more or less based on instruction sets, right? So.
And you guarantee that here you are using the most, the most powerful or the most convenient instruction set for the machine.
For the one we have. So it's not exact. It might not be exactly right, but it'll be the best that we can do. Right, so what we have, based on what we have, here's what fits here, right? So if that's like if you have a Skylake or Cascade Lake, then it'll use the AVX512 instruction set, and you're missing out on nothing, right? So that should be the same. And so that was the demo part, right? So that's lots of the examples that have been run here now. Let's go back to the presentation. So that's just to show you how quickly you can have the full environment up on that system. Now you have to remember, right, that I just showed you a couple of examples, but there are many more software packages already inside the pilot. And the idea is to expand this to thousands and thousands, right? So we'd have lots and lots of... So in EasyBuild itself, I think it's like we're at around 3,000 packages, 3,000 software applications that we support, not including all the Python and R extensions that we have.
Yeah, but you never will cover all this space. So as a user, I can compile my own.
Yeah, you can build on top. So the idea is it's extensible as well, right? Because for us, what can we ship, right? You have to think about the limitation that we have. There's a limit on how much we can ship, not only in terms of the number, but also in terms of licensing and things like that, right? We're not allowed to ship everything, right? So because it's built, the software layer is the backbone is EasyBuild, right? So we have a configuration, we have an EasyBuild configuration that will allow you to build on top of what we ship, what we already ship inside EC, and then you can add additional software on top. Yeah, it can be anywhere, because at the end, you have to think about like this, what I showed you, CVMFS, it's just a location on a file system, right? Now, it happens to be a distributed file system, which means you can access it from anywhere. But at the end of the day, it's just a location on a file system. So you can take your compilers, your MPI, everything from that location, and build your own software and put it somewhere else, right? And we want to make that as easy as possible as well. So we want to ship a configuration where you can do that using a recipe, you install it somewhere, and actually it will automatically appear as well. So you don't have to interfere with the module path or anything like that. There are tricks we can pull to make that possible too. Yeah?
So I see that you have in this file system, you have the combinations for different architectures, okay?
Yeah.
And this is what you mount, so to say.
Yeah.
And you have the binaries there which you can use in your system. But how do the modules, I see that you have the modules for Haswell only. How does this work?
No, you have the modules for Haswell. The ones that you're using are Haswell. But the other ones are all there. So if you go down to that directory, so this location where you see Haswell, if you look inside, you'll see the Skylake one, you see AVX512, you see... No, because it's only showing you the ones that will work on the system, that work best for the system you have, right? What? Oh, because we run it. So when you do this, when you source our initialization script, the first thing it does is check, what have you got, right? And then based on what you've got, then I'll use this particular environment, right? But the idea is that inside that module avail, then you'll have the same software packages, right? So whether you're on Haswell, I'm on MARM, we see the same things, right? And then, so it means like if you have like a workflow, for example, I say module load GROMACS, and away I go. And it doesn't matter if I'm on ARM, it doesn't matter if I'm on Haswell or Skylake, I should get the best executable for where I am right now. So in this case, what we did was we went through and we installed CERN VMFS, we installed the EC configuration, we did a very minimal setup of our client so that things would work. And for production usage, it's a little bit different, especially when you're going to large scale. Now, I was even surprised myself at how fast everything was in the AWS environment. Usually it's not as fast as that, but it seemed to be really, really quick. I would say I didn't notice any really overhead to us at all. Usually you see a little bit more than that, but to get around, to make sure that everything is as close as possible to where you are, whoever provides your infrastructure can improve the performance, right? So they can use what's called a squid proxy to do caching locally close to your system, right? So that improves your network performance. And already on your client, on the client itself, you have local caching as well, right? So, and you can dictate the size of that cache. So that was one of the things we did in our configuration setting. We said that, I think it was 5 gigs or 10 gigs we made available as a cache for all the files that we want to keep locally. But then you can use a squid proxy to make sure that for your users, there's lots more stuff available. If you're concerned about network outages, you can make your own Stratum 1, so which is a complete copy of everything that we ship, and have that locally on your system itself, so within your own network. And so, for example, if you didn't have, say if you're in an HPC system and you don't have internet access from the compute nodes, this is a potential solution to that, right? You just make a complete copy of everything. There are other ways of setting up the caching. There's something called an alien cache as well. So if you don't want a Stratum 1, but you don't have internet access on your nodes, there's another way of setting up caching. Also, there are lots of ways of facilitating you, so you don't necessarily have to have network access to access the software that's there. In general, these things are good ideas, right? So these quid proxies, and if you're a heavy user of Stratum 1s, they're a private Stratum 1s for you only, say. They're good things to use because it means that you won't become be a bad citizen on our wider network, right? So, and we have ways of monitoring that to see people who are using things a lot. So, for example, in Azure and in AWS, we have Stratum 1s already, so you can get stuff that's quite close to what you're using. So we looked already inside the script that was inside. It's just installing a couple of packages or a repository if that's available, which is, of course, the better option because that means you automatically get updates to CVMFS as well. The two things that we put inside our configuration file, the one that dictates the size of our local cache on the system is the CVFS quota limit. So in this case, it's 10 gigabytes, what we put in here. So we say, like, up to a maximum of 10 gigabytes, that's what you can use for software that you're caching locally. After that, then there's a replacement mechanism used. And the client profile, I actually can't remember what that means, but I think it means you go directly to Stratum 1 to get the files, but I'm not 100% sure. And then we looked at the software that was available in there. So how exactly does it work, right? I gave you this kind of overview picture before, which is like a bit hand-wavy about how it all works. Let's look a little bit more into the details. So CVMFS, right? We learned about these, we heard today already about these kind of fuse file systems. CVMFS is one of those. It's been around for a while, and it's used by a lot of people. Because it's developed by CERN, and they use it to distribute their own software, right? So there's a lot of people who are analyzing data that's coming from CERN in lots of different places. They needed a solution to make sure that everybody's using the same software packages to do the analysis, and CVMFS is what they came up with. How does it work? Well, it's a global distribution of these software installations, and then you centrally manage something. So that's the Stratum 0, which is like the master copy or whatever, or the global copy, whatever you would like to call it, the main copy. From that, then you make copies. So they're called Stratum 1. You make a redundant network of mirrors. Now, you'd imagine in this case that more is better, actually, but actually they say that there's a sweet spot of around 5 public copies. That's probably enough for your system, probably enough for the distribution, and then people can have local Stratum 1s as well that's only available inside their network or to their users as well. There are multiple levels of caching, so as I said, you can have your own private Stratum 1, or you can use a squid proxy. Squid proxies are very common, and they might be good for inside clusters. If you if you want to serve a lot of nodes, rather than all those nodes asking for files individually, so that's a very good idea. And then we have the same software stack that's available everywhere, right? Because everyone sees essentially sees the same file system. Okay, move. So the next layer, that was the file system layer. The next layer up is the compatibility layer. For this, we use Gen2 prefix. So we put it, Gen2 prefix means it's Gen2, but in a particular location on your file system. So as we said, as we've seen, CVMFS is in a certain location. Gen2 prefix allows us to install an operating system into that location. So that's what we do. It's tools and libraries, and it's in a non-standard location. We try and limit what we provide in the compatibility layer. So the idea behind EESSI, the original idea really comes from Canada. They've been using this for about 10 years to provide all the software on the systems, on the HP systems that they have in Canada. And so basically we've taken that, we've changed it a little bit, tweaked it, say, and we've expanded it to an awful lot more architectures and opened the door to allowing a lot of people to add software. But the idea is essentially theirs. They've been using it for a long time. So they provide a lot more stuff in the compatibility layer than we do. We try and keep it minimal. But it does include things like glibc, right? So we don't have Linux kernel, we don't have drivers, but we do have glibc. So yeah, you can think of it the same as the OS layer in a container image. The compatibility layer is not built for performance, so it only targets a family of processors. So we only have a limited number of those, right? So whether that's ARM, or Power, or x86, or RISC-V. What that gives us then is a level ground on which we can build a stack, right? So regardless of the operating system that you have, it looks the same to us. And then in the compatibility layer, yeah, we have these three. We have three right now. So we have ARM, we have Power, we're dropping Power, and then we have x86 as well. So the software layer, that's where we actually build software. That's where we provide all the applications, all the libraries, and all their dependencies. These are optimized for specific microarchitectures. So that in our case, the one that we're using, the one that you have access to is Haswell. I just showed you that we also have the ARM support there. And each of those architectures has a different subdirectory or tree underneath the CVMFS directory. So if you look inside, and the one that you have available, if you load a module, you see, if you look at your path, then you'll see that it's coming for a particular location that's specific to the architecture, and then there's a software directory inside there where it's actually pulling the software that you use. It leverages the libraries that come from the compatibility layer, and that was the tweaking that we've had to do to EasyBuild to make sure that that is the case, right? So we do not want anything coming from the host in terms of these types of libraries. Nothing comes from the host OS. Everything is coming from this compatibility layer that we have that allows us to ensure that we can move these executables will work on different operating systems. We install things with EasyBuild. So as I said, the initiative in general comes from the EasyBuild community. And then we make software available through environment module files. And the tool that we use to provide those is LMOD, right? So this is like the user interface to right now to what we have. It could be different in the future, but LMOD is what we use right now. The best directory for the host to use, that's selected automatically by a tool called ArcSpec, which kind of looks at your hardware and then categorizes it according to some parameters. So we select that according to what ArcSpec tells us. We are building a little bit lighter version of ArcSpec to do the same thing, but just using bash scripting because it'll be faster to run. So that's already, I mean, it's already included, but it's not the default right now. So big question, of course, does it scale, right? So we had a paper. It's a while ago now, actually, but it's an open access paper. You're free to look at it. It has an awful lot of, it's very, very large, has an awful lot of information inside. But one of the plots that we included in here that might be hard for you to see here because they're small dots, but basically we looked at, again, GROMACS. We looked at the nanosecond simulator per day on a system in Jülich up to 16,000 cores, right? So we had 2 to the 7 nodes, and there's 128 cores per node. We compared the performance that we get from EESSI, from the EESSI compiled version of GROMACS, to the one that was offered by the system, right? So they weren't compiled in exactly the same way. That wasn't the point, but it is the same version of GROMACS, right? So they're compiled differently, but the version or compiled with different, like for example, MPI stacks. One was with PowerStation MPI, the other was with ours is with OpenMPI. But it's the same application, right? So the same use case. And how do they compare to each other? So the red dots, the black dots is the EESSI version. This is a Zen 2 architecture as well, right? So this is an AMD system. So the black dots are the Zen 2 version of EESSI. The red dots are the stack that comes from USEF itself. And then in kind of a blue, there's the x86 generic stack. So not optimized for the architecture. So the point of including that was to show that it makes a difference, right? So the performance that you get is dependent on the architecture. We can see those blue dots are consistently below what you get for the optimized numbers. What is interesting is that we compare very well, certainly within error bars, with the host operating, with the software that was provided by EESSI itself. And in some cases, the problem is it's not relevant. As we go to larger and larger node counts, we actually got better performance than what was available on EESSI, but it's kind of within the noise. I don't think it's really relevant. The point of the experiment was to show that we can compete, right? That it's not that that the use of EESSI comes at a cost. That's not the case. Certainly not necessarily. Yep.
I'm sorry, here you say that you are using two MPI different MPI implementation. When you are scaling, you can have a great impact. So it's not only that the binaries are different, but you have one part of the application that can really make the difference, and it's not the same.
Yeah, but in this case, think of it like this is a black box, right? So you're taking GROMACS from us. You're never going to compile it yourself. You're a user of GROMACS, right? So the system is providing GROMACS, and we are providing GROMACS. All that's presented here is a comparison of your input data set with the version of GROMACS run with the system one and the one run with EESSI, and to see how they could compare. And the fact is that the performance is the same. Yes, the MPI layer is different and probably could be tuned, right, with some parameters, right?
No, my point is that I think you could do it better than you could even reach the performance of the software stack.
Yeah, so we tried to make that clear. We actually got that as a comment in the review in the paper as well, about trying to dig into the details. What was the difference between? The kind of point is, it doesn't matter, right? In the sense that you're thinking about a normal user, right, who comes onto the system, who may, in the end, look at things like how to tune the MPI layer, but many, many people do not do that, right? They just take what's available there and run, right? And this is to show that even on a scalable application, so even in the case where you want to use the fast interconnect, you can, it works, right? You can provide something on multiple sites that would work on those multiple sites. So what's the current status of EESSI right now? So yeah, it's a working proof of concept. It's been there actually for a couple of years at this point. We're about to move to production, say like some kind of production-ready status this year. So there's lots of Ansible playbooks in there about how to set up the infrastructure. Everything we do is open source. You can see exactly how we do things on our GitHub repositories. Our CVMFS setup, our Stratum 0, so our main copy is at the University of Groningen. And then right now it's 4, it may even be more Stratum 1 servers that we have in different locations. We put software in place that either people use or is complicated to install from source. So I don't know if anyone's ever tried to install OpenFOAM or TensorFlow from source, but it's a little bit hard. Right? So we did those on purpose, right? And then we included packages like R and all the extensions that we have for R, which are thousands and thousands, right? And they're also available there just to show that they are good for different communities as well. We have those hardware targets that are available, but we do plan to expand those as the use case arises. So we have Intel, Haswell, Skylake, we have AMD, Zen 2, Zen 3, we have ARM, we have Graviton 2, Graviton 3, and we also have, what's the new one called? It begins with A. I can't remember now. And then we have Power as well, but we're dropping support for Power, because we don't see many people using it, and it does kick up problems from now and again. We get support from Azure and AWS, so we get quite a few sponsored credits to help us to develop the infrastructure and to support things like our distribution layer. So now it's your turn to give it a go. So this is the hands-on. So this is running a demo. It's basically what I've already done for you, but you're going to do it on the infrastructure that I provided. So in that infrastructure, you don't need to do any configuration. EESSI is already available. You can see all the modules that are inside. You can load them, and you can run them. So the thing that you need to do is you need to actually clone the repository. So I'll leave this slide up here. You can clone that repository locally, then go inside, and you should already be able to run some of those tests, right? So if you want to run the GROMACS example or something like that. With the GROMACS one, there's also a Slurm script included. So if you wanted to submit it to the queue, you could do that. But you would need to tweak it if you do that, because there's only 4 cores per node. They're tiny little nodes, right? So you need to tweak that submission script. But I'd like to give you a couple of minutes to give it a try. And then for anyone else, if you have any questions right now, you can ask. And there's a couple of people in the room to help out as well. So if you have any other issues. Yeah. Yeah, yeah, we've done it in Raspberry Pi. So we had TensorFlow running in a Raspberry Pi. Yeah. Huh? Oh no, it was very slow, but no, but I mean, try and compile it, right? It's impossible, right? Because you need so much memory. But we can compile it and run it in a Raspberry Pi. We compile it somewhere else and then run it on a Raspberry Pi. Yeah. The same with the RISC-V stuff. We could already start to compile stuff because we can use emulators or we can use something else to compile for RISC-V. The thing is, you need something with large amounts of memory, right? So like compiling something like GCC, or there are some applications that require like enormous amounts of memory to compile, and you don't get them. You don't get that. The hardware doesn't exist, right? So how do you do that?
Because then the idea of EESSI is having like a batch or a bunch of those resources then to do the deployment and then to upload to this same FS, or how you want to continue to expand the number of...
Oh, yeah, that's coming next. So how to add software is the next part of the presentation.
Yeah, because for the civil, I understand that I send you, I contribute with the reset,
Yeah.
but for EESSI, how...
Yeah, I'll show it. That's next. Yeah. Yeah, the reason Mac is difficult because of the glibc. We actually had a compatibility layer that worked on Mac, but we're going to have to do it based on the OS. So we can't do it's a bit more complicated because we're stuck with the glibc that they offer. And I mean, it's a solvable problem, but we haven't. It's not worth the effort of our effort right now. So we looked at it before. We got a compatibility layer, but it's effort that's not worth it for us right now. Yeah, whatever they have, yeah. So basically, I mean, you'd have to look at the CVFS instructions about how to get CVFS working on WSL. It's not that complicated. I mean, because you're just inside. It's not that bad. We just have to do, when you go into a shell there, you have to run a certain command to get CVFS working. But then once it's there, that's it. Yeah, that's it. Oh, sorry, yeah. That one. Yeah. No, I mean, what would I do in practice there? You have to be a little bit careful in that scenario, right? Because order starts to matter. Yeah. Yeah. So you can have both, but you might want to choose. So, for example, if you have two different stacks, if you have your own stack plus the other stack, you might want to have a gateway module that says go this way or go that way, because not for any particular reason, but because they can get in the way of each other, right? So like you accidentally start mixing and matching, and maybe it doesn't work out for you, right? Yeah, but the EESSI stuff is unlikely. It's not going to break, right? So any executable that you run from EESSI everything is RPath inside, right? So the EESSI stuff will run. But then once you start mixing and matching libraries from different places, then you've got different libcs, right? And it's not going to work, right? So if you're building something, you have to be careful that if you build on top of EESSI, you can't mix something that you have locally with something from there, because it's effectively trying to mix things from two different operating systems. I just give it another minute, and then I'll go on to the next, because we're already behind, as it happens. So yeah, if you have an issue, just raise your hand.
So these modules that
Where what? Where?
where the module path is set.
No, the sourcing. So that you source a particular. Let me go back here. So you can go and have a look inside what it's actually sourcing there. But say, yeah, where do I have it here? I don't have it here. Yeah, here it is. Yeah. So this one. So you're sourcing a particular location. You're saying, oh, yeah, init bash, right? Yeah. And that basically, that's the one that selects the architecture, and then it says, oh, use this path, and then. I guess we will share these slides somehow, right? So there's some other information, some links and stuff that will be useful. Yeah, it's 20 past 30. So if you want to try it out, like inside Singularity or Aptainer or something, that's also possible. And you need to set a couple of environment variables, so I couldn't fit them on the slide here. So you can just go to have a look at our documentation about how to do that. But basically, you just need to set 3 environment variables, and then you can run our image. And it's very, very lightweight, our image. Our image works on 3 different architectures. And then it'll just, the software that you use, it'll just pull it in dynamically, right? So basically the image itself, I think, is 100 megabytes for something that maybe is user-facing for potentially many, many gigabytes of software itself, right? Okay, so we already had the question, which is good, right? So like you have software in there, but I want my thing. How do I do that, right? So how do we add software right now? So our workflow is unfortunately too human-oriented. So some human runs the software installation script inside a special build container that we have for each of the target CPU architectures that we have. That human then goes off and creates a tarball with the new stuff that we've added on top and uploads that to an S3 bucket. Then we've got a script that looks inside the S3 bucket and pulls those tarballs, creates a pull request to a private repository that we have on GitHub, and then when that pull request is merged, then the application gets included in what we ship in Stratum 0. So that's ingested into our pilot layer. The scripts that we use, they're all available in different locations depending on what we're talking about. So if we're talking about building software, that's the software layer, or if we're talking about something that's related to the infrastructure, it's somewhere else. But basically the install software layer script, that does the installation of something on top. We've got that build container, which allows us to get a build environment that we're happy with minimal stuff inside, so nothing interfering with our build processes. And then we have something that creates the tarball from what we've built, and then it uses basically what's called a fuse overlay FS. So basically, CVMFS is not writable, right? When you're a user, it's a read-only file system, but you can use fuse overlay FS to put something that is writable on top of it. Right, and so basically we install into this overlay layer, and then we tar up what's in the overlay layer, and then replay that back onto the Stratum 0. Right, so that's how we get exactly the same thing that we built, and then we upload that to our S3 bucket. There's many problems with this, right? It's far too manual. It's time-consuming, so there's lots of human babysitting, and you have to take action based on that. It doesn't allow low-effort contributions from other people. Who are not already familiar with how we do things. And then, of course, you actually need access to all this growing number of target CPUs. So we've got all these different Intel, AMD generations. We've got all the different ARM, specific ones for AWS and Azure as well. And then we're also looking into RISC-V. So, of course, you obviously need permissions to upload something to our S3 bucket because we need to trust you. And then we need to know who provided the software builds, and how do we know they actually weren't tampered with in some way, whether somebody knew what they were doing or they didn't, right? So our idea is to automate all this, right? So we have something that comes from a contributor, a pull request, that's reviewed by, so that's just, usually it's a text file actually that you will edit, right? A reviewer will look at that and say, that's okay to me. And then we've got a bot. The idea is that we would have a bot that would go away and build all this stuff, test it, create the tarballs, upload them to the S3 bucket. When the tarballs are there, there's a cron job that will try and play them on top of Stratum 0 and make a pull request. Somebody will review that pull request, and the bot will take over again and put them into the repository. Right? So automate as much as possible, but make sure we have human oversight in the most important places. So how would we actually go towards automating this, right? So we want to allow people to easily contribute additional software to EESSI. We want it to be low effort. So the idea is that it's just a pull request to GitHub. We want there to be automatic feedback on whether the integration actually works. And it might not be the case, right? Not every software package will work on all the architectures, and issues will arise, right? So we need to be able to get that feedback as quickly as possible, and then look into how we might fix that. The place we have to pay attention to are the automation, the performance, obviously, of the software that we're building, the security of our whole setup and everything that we provide, and then we want to minimize this amount of human oversight that's required. So what are our conditions for accepting contributions? Well, the software should work in our environment, right? That means that we use the compat layer, we use our path everywhere. We're going to have a very long prefix, unfortunately, but that's the case. So it needs to work with that too. And then ultimately, especially for marquee stuff, we want to make sure that there are tests included so that we can test the end user applications. Not just for correctness, but also for scalability and performance as well. So we want to work with people to help create tests with Reframe, especially for big applications, things like GrowMac, things like OpenFOAM, like CP2K, like Quantum Espresso, these applications, or Wharf, things like that, to make sure that they actually work the way they're expected to work and that they work at the scale that they're expected to run at. And then we want to have the software builds and the tests on those builds. They should pass on all the targets that we have access to as well, the CPUs. To do that, then we've started implementing. It's a large part of it is already implemented. A GitHub app that does that for us. So it's built using, I don't know anything about these things, but it's using Flask and PyGitHub to talk to the GitHub API. It works on the basis of events, so it reacts to the pull requests that are created. So whether that's opening a PR or posting a comment to a PR, adding or removing a label, it does things based on the action of a trusted person. And the tasks that it runs are like automatically building, installing for the different target CPUs. That's just building, right? So we're not worried about that. That doesn't need human intervention. It uses the build container. It makes sure we're very careful, obviously, that it's using the compat layer as well. We run tests, and then it can run tests to verify that the software installation actually works, both on the system where it was built and also on different operating systems as well. And then the last part of its job is to go away and take the software installations and have them ingested into the EESSI repository, and after some conditions are met, obviously. So let's look at that picture, how it actually works. So right now, anyone who's used EasyBuild before will be aware of the idea of easy configs, right? Which are basically kind of like a low-level recipe for how you build a piece of software. We now have support, it's still experimental, but it won't be for very long more. It'll soon be part of main EasyBuild, something called an EESSI stack file, where you can describe a lot of different easy configs in a single file. Say, like, I want a stack of this type of environment, including this package and this package built with these commands, and that one built with those commands in a single file, so a single YAML format file. So as a contributor, you would come along and you would say, I want this software, OpenFOAM, built with this tool chain and that version, right? Two versions, version 8 and version 20. I actually don't know what that means, 2006. Anyone who's familiar with OpenFOAM knows there's a couple of different variants of OpenFOAM, so you might want one or the other variants, right? So that's what you as a contributor, that's the change that we will make. You'll just make a simple change to a YAML format file. And then if a reviewer okays that, the bot will come along and say, oh, yeah, I see an approved review for this PR, so I'll go away and build it, right? So the bot will go away and build on all the different architectures and create tarballs for those architectures. He'll come back and he'll say, hey, yeah, those builds were okay. Everything was fine with building all that software. And if that's the case, then we can think about the testing, right? So we've moved now to testing this environment. So let's say there was also a test involved for OpenFOAM. So we have a set of reframe tests that we can run. So we say to the bot, yeah, that's good. Now go away and run the test for that software. So the bot will go away and run the reframe tests on the system where it was built, but also on a number of different other test systems, including different operating systems, right, in those systems. And then the bot hopefully will come back and say, yeah, I ran all the tests and everything was okay on those tarballs. And next, the reviewer will say, great, if that's okay, then the PR is merged. The bot will go away then and upload it to the S3 bucket. Then it'll get downloaded to work on top of, again, it'll be tested at the top of Stratum 0 and ingested and made available through EESSI. Right? That's a simplified case, right? But that's the idea of the workflow in general. Yeah?
The stack file that you show, this at the end is translated to different EESSI files.
Yeah. Yeah. So this is a very simplified view, right? Because it wouldn't it be great if you could just say, I want OpenFOAM version 8, and it just works, right? It's not like that. This translates in the end to an easy config file, right? Which is a full detailed recipe of what this software should look like. So if you have a new software package that isn't supported in EasyBuild, you won't be able to do this, right? The first thing you need to go is get that software supported in EasyBuild, and then you can make this change here. Then you can say, right, I have this recipe over there, so just give me this version of that software.
And does it have the logic, for example, if I ask another version that it's, imagine that you have this in config for version 7, if I ask 8, this has the logic to be the easy config file for the...
I mean, you could try it in the sense that it's the same as all these try options in EasyBuild, right? You can give that option of try this. Yes, you can do that, yeah. So you can give all the options you can eat to EasyBuild, most of the options, you can give them inside an easy stack file as well. Right? So these questions are a little bit specific to how EasyBuild works, but at the end of the day, this is the tool that we currently use underneath, right, to build the software. So it's an important layer. So the use cases that this enables, right? We believe that there's a lot of them, right? There's the first and foremost is the uniform software stack, right? That's great. The other thing that once you have something like this, then lots of other things become possible all of a sudden. So if you can imagine, for example, portable workflows, right? I have lots of software that I need to use to run my workflow, and I want to run it in everywhere I have available to me. So this, because we have a portable software stack, this becomes pretty straightforward to do, right? Or at least conceptually, it's very straightforward, right? I have an environment that will work no matter where I go, so my workflow should really work in all those places out of the box. The other thing, it can be leveraged in continuous integration environments. So, for example, you could imagine one option there, of course, is like a build environment, right? I want to build a software package, or I'm developing a software package. EESSI can very, very quickly provide the environment that you need to build your software. So I need CMake, I need this version of GCC, I want OpenMPI, I need these math libraries, I also want HDF5 and PETSI, for example, something that's really complicated, right? I want all these things to be able to build my software package. EESSI can do that for you. So in seconds, you have the environment you need inside a CI environment. So all you care about is running my own software, right? The other thing is HPC training, right? So because we have the same environments, regardless of where we're running, then HPC training becomes easier as well. We don't need to give people access to the production resource to train them on the software that we have available on the system. They can do that anywhere, right? It might be in a VM, or it might be in kind of like the environment that I've just given you on a kind of a pseudo cluster in the cloud or something like that. That's all possible now. And then the other thing is it opens the door to enhance collaboration with software developers, right? So if you know that a package that gets included in EESSI is going to be used by a lot of people who care about performance, then it gives you a focal point where you can say, well, I care enough about the performance of my software that I'm actually going to do all that hard, very, very hard performance analysis work to see how I can improve it. Because if I do it here, all of the people who use this environment will benefit, right? And if you do good testing, so if you do good, like if you create good reframe tests for the environment, and we agree, and we run them, right, and you know that we run them, then you can make these changes, and we can cycle through different options here and test them out and see, will they work? Will they pass all your tests? And so that's something that's interesting as well. And so all of these options, all of these things are also discussed in this open access paper. So yeah, we said this already, right? The uniform software stack, hopefully it's clear that this is a big advantage, right? So regardless of the architecture, we get something that works and works well. And we don't compromise, right? So we have something that's optimized for what we have access to. And then, of course, obviously it facilitates this migration for a user, from whether it's from their laptop to a server, to HPC, to also doing cloud bursting, right? If you know on the local system we have this software stack, and I get exactly the same software stack in the cloud burst system, well, that's great for me, right? Because I don't need to change anything in that sense, in the software sense, right? And anything that gets added is automatically added in the other environments as well. The other thing that EESSI can do is this portable workflows, right? So that in theory, at least, they should be easier with EESSI. They usually involve lots of different tools, and all of those tools need to be available. The other things that we can ship inside EESSI is actually these definitions of these workflows as well. So whether it's Snake Make, Nextflow, or some other environment, they can be either EESSI can be leveraged by those workflows, or they can even be included inside EESSI itself, right? You can actually ship them. One kind of trick that's nice is that you can actually ship your execution environment inside your Git repository if you use a tool like direnv. Right, so basically that means that if somebody clones your workflow and you have used the tool direnv, and so have this special file inside, we'll see it now in a second, then they can actually enable that environment the second they enter your repository. Right, so basically they can get the software, things will work right out of the box. Once they enter the folder, they get the environment and they can just start running things straight away. And we're actually going to do that right now. So that's our second hands-on. We're going to ship a workflow, very, very simple workflow. Right? Yeah.
What is your long-term guarantee on the availability of the software? So you mentioned about this portable software, but I'm just envisioning someone publishing a paper based on software that is available in EESSI, and you want people to be able to reproduce it some years after. Will you guarantee that the software that I'm using today will be there in 5 years?
Yes and no. so the idea is, right, so one of the things we've discussed this, right? What we've discussed to date is the idea is that if we say like we do them, the way we do pilot now is we have like different pilot versions, right? You can imagine that like if we think of the compatibility layer, like we want to change that at some point and update it, right? So then you have a different branch. You have the old compatibility layer, like a different operating system, right? You have the old operating system and the new operating system. Now, eventually, there's going to be a lot of these, right? And we'll say, now it's time to retire this one over here, right? In that scenario, there are things that you can do, right? So you can do, so in CVMFS, there's something called a variable symlink, right? So what you can do is you can replace a directory by a variable symlink, which is part of your configuration file, right? And so one of the ideas that we had is that if we retire, say, an operating system, if we retire that, we replace it by symlink to a file that tells you how to put that back in place, right? So go to this place, get a squashfs file, and then put it in this special location, change the configuration file for that symlink so that it finds that location, and that's it. Right, now you have that available, right? So basically, we can archive it. So we can put it into squashfs, archive it somewhere, and then give you the information that you need to put that back in place for that system. So not globally, but wherever you might want to do some reproduce something, then it would be available to you, yeah.
Have you considered creating an archive CVMFS repo?
No.
Where you would just move the whole version?
So the benefit of doing it that way is no paths change, nothing changes, right? But if you move it to a different location, then you have a different path, right? You could rebuild.
But then you can use the variable symlink to point to.
Oh yeah, you could do something like that, yeah. No, we've never done this in practice yet, right? So we haven't got to the point. We have ideas about how that's one way it could be done. There are other options, right? That might be better options, right? So because you could protect. For example, for a Stratum 1, you wouldn't want them to keep cloning stuff that's from 10, 20 years ago, right? So the idea of an archival location where you just have squid access or something like that might be a good idea, right? Yeah. So we haven't. Yeah. I think it's a space where there's time to think about these things. So I want to do this example. So I have another Git repository that I'd like you to clone. So it's this location. So it's the EESSI organization again. And then it's EESSI-nextflow-example. And I'm going to do 2. Get out of here. So I'm going to take that location. I'll stick it into, I don't know if any of you are using the Slack, but I'll throw it in there just so you have it. Actually, I need to. Come on. EESSI Nextflow. So I'm going to clone that repository. And we go inside. Okay, it looks like there's not much in here, just the Nextflow workflow. But there's actually something else as well. There's something to install the DRM tool. So depending on your OS, it's pretty easy to install DRM. So on Ubuntu, you just do apt-get DRM and it'll work. But inside this one, it gives you kind of an OS independent way of installing it. But it's a bit invasive, so I didn't want to make it visible by default. But there's an installation script for DRM. So basically, it pulls down an installation file, which you may or may not trust, right? Obviously, and then it installs the DRM tool, and then you run an evaluation. This one puts it inside your bash RC, so DRM is also automatically enabled when you log into the system, but it's also running it locally. So when I run this script, so let's run it now. I source it because I have that in it. Mycell.install DRM. It'll go with it, pull down a file, install it, very, very quick. And now I see this red message at the bottom. It says, DRM, oh, you're in this place. I found this envarc file, but I'm not going to use it because you haven't allowed me yet. So it's a bit protective, right? It's saying, I'm not going to automatically do stuff unless you tell me to do it, right? We can have a look and see what's inside this .envarc file. Very little in this case, right? But it could be anything, right? So one thing it does is it's sourcing EESSI, and so it's making EESSI available. A particular version of EESSI as well, so maybe I don't want the latest version. Maybe I want to stick with a particular version of EESSI because that's the one I know works with my system. So I've sourced a particular version here. I'm going to make sure there's nothing else in my environment, so I'm going to purge any modules that might be there. I need a couple of things to run this workflow. I need Nextflow itself, so I module node Nextflow, and then I also need Gromax because Gromax is required as part of my workflow as well. All right. So if I do DRM allow, that will mean that DRM will actually go and run those commands for me. And so you can see this is the message that you get. So you say, oh, DRM exported all these different variables, right? It looks like a lot, but it's basically exactly the same. It is exactly what the module command does as well. You just don't see it this way. All right. And now, in this place, I have the Nextflow workflow, and I can go ahead and run that straight away. So everything I need for the workflow was defined in the envarc file. When I entered the directory, if I allow it to do it, DRM will load all that environment for me, including any environment variables that I choose to set. So it might be things like, I don't know. If it's a compiler, if I'm doing a build environment, it might be compiler optimizations or something like that. Excuse me. And yeah, it's running a little bit slow, probably because I only have one core, I think, or 2 cores on this system. I don't know, is anyone else running? I ran the same thing on the AWS instance, and it was instantaneous. But it will run eventually here. It just seems to be a little bit slow. So what it's pulling in to do this, there we go. So there's Nextflow running now. It's pulling in Nextflow, and it's pulling in Gromax was probably already available because it ran very fast. But that's it. There was 4 tasks in this workflow, or 5 tasks. Yeah, 4 hello world kind of tasks, and then 1 that just prints out the version of Gromax, right? But it's just to show that if you have a repository that defines a workflow, you can ship the environment to run that as well. So I give you a couple of minutes just to give it a try. We're nearly out of time, so it'll only be a few minutes. But
CVFS transported through NFS to the nodes?
No, you would. I mean, the way you would do it is to have CVFS on the nodes. So on the nodes. So you would have it like the idea being that, you would have it on the nodes, and then you say one way of running things would be, for example, you would run a squid on your management server or something like that. So the nodes would talk to the management server. Everything would be cached by the squid on the management server, and so everyone gets the same files rather than each of them going to somewhere else and downloading an individual copy, right? And then then I mean, the typical question is like, I don't want this CVMFS running on my nodes. Can I do something? And the answer is yes. Right? So there are a number of different ways of doing it. You can use something called an alien cache, which means which means you effectively pre-populate the cache with everything for your system. That could be effectively like a copy of the entire stack, but you're probably not interested in everything, right? Because I have this architecture, right? So you say, I want everything in this software directory for this architecture. That's all I want to cache. And CVMFS has deduplication and everything, so it's not going to be enormous, right? So you're talking about like gigabytes, right, or a maximum of a terabyte. In the HPC space, this is peanuts, right, in terms of things. So you're not going to get huge amounts of, you're not going to need a lot of space to store this stuff, and then you can just provide an alien cache, which means you would still, in that scenario, you'd still have to have CVMFS running on the nodes. But there is another option again, which is like, at the end of the day, it's a file system in a location, right? So long as you can guarantee that location somehow, then it's available. It will work. It just has to be the same location. So you could do that, for example, through SquashFS. So you could say, pack this stuff up, make a SquashFS, make it on the nodes, and then there's no communication over internet at all, right? It'll just load the things. But that comes at a cost, right? So also you lose a lot of some of the features, right? The good things, right? Some of the caching layers. You have to have a copy on all the nodes. It might be big, or else you're mounting it from NFS or from some shared file system or something like that. It depends on what you care about, right? So some people, the typical thing that I hear is, I do not want another service running on my compute nodes, right? And this is another service. Now, surprisingly to me, CVMFS hasn't looked at the jitter impact of CVMFS on the nodes. And that's something that I would like to do with them, that I think they should know, right? They should be able to answer that question, right? Will this introduce jitter if I have like many thousands of nodes running the same executable? They say no, but it's not enough to say no, right? You have to test, right? But even in that scenario, the point is that there are ways around it, right? So if you have thousands and thousands of cores, you can afford to store a file that's a couple of gigabytes in size and SquashFS or however you want to do it, make it available on that system, right? Well, I mean, you could do it. Yeah.
You can have client that export
Yeah. We've only got a couple more minutes, so maybe I'll finish up. Did anyone try that out? Did anyone have any success? Yeah? Good. So the other one was CI environments, right? So you've seen it for a workflow. What's a build process? A build process is also a workflow, right? So you can use it in CI environments. We could provide, for example, different compilers that you might want to use to test your build for your software, any dependencies that you might have. We've got all that other tooling that might be interesting for you, where things like Reframe. We could provide performance analysis tools as well. Other than CVMFS, you don't need to do any other installations. They'll be pulled down on demand. And so this significantly facilitates CI in other contexts, whether also like, yeah, you can have the same CI context regardless of the system that you have. So whether it's in GitHub or whether it's on your laptop or in an HPC space or something, you can run the same kind of tests. And we have an action for this. So there is already an EESSI GitHub action that provides EESSI and the DIREM tool as well. And so hopefully some of you have used GitHub Actions before. So basically it's a YAML format again. You do the checkout. We have our own EESSI action. And then you can there are options you can give. By default, it'll just use the latest, but you can also choose which version of the stack that you want. And then once the stack runs, then you can run whatever you want. In this case, it was just printing out the version of Gromax. It's probably really hard for you to see here, but the point of this is that action working. The point here is to see that everything is in place within a minute, right? So you have all of the software that we ship with EESSI is available within your CI within a minute, including your compilers, including your dependencies. Everything there is ready to go. And it will be cached, whatever you might be using will be cached locally as well, so it will be quick, right? That's the point. So you get everything that you need within a minute, right? It's a lot faster than trying to do Yum installations or something like that within your CI. It's definitely going to be an awful lot faster than that. So next, it facilitates the HPC training, reduces the effort that you need to set up infrastructure to support that. So you can do lots and lots of different things. Easy to do introductory training, a great place, a good way, hopefully, of doing software-specific training. And then setting up a throwaway cluster in the cloud. There are lots of tools out there that allow you to do this. We heard of one of the commercial, or I don't know if it's commercial, open source, some of it's open source today. Clustering, there's other ones called Cluster in the Cloud or Magic Castle. Today, the system that you're using is Magic Castle. That cluster was created by editing a single file, and then you also have to have some credentials as well to allow you to do certain things. But basically, you just edit a single file. That entire cluster was up and configured, including Jupyter Hub and all the other bells and whistles that are in there, within 25 minutes. Right? It took 25 minutes to set up the whole cluster, and the entire software environment is there. Magic Castle as well supports GPUs and fast interconnect. So I've tested it with InfiniBand that you get on Azure and also with EFA on AWS. Both of those tools, the open source tools, this Cluster in the Cloud we use for the bot. Cluster in the Cloud is good because it allows you to have different partitions with different architectures. That's how we submit lots of jobs to different architectures. And they auto-scale as well, so they disappear when we're not using them. But it doesn't have multi-users. Magic Castle is really good for training. It's been developed by Canada. It was designed for that purpose. So it has all these bells and whistles like user sign-ups, and does all the web-based things as well. It has Jupyter Hub. It has all these nice features, including things like RStudio and IDEs as well. There are, of course, commercial options that that either do or will support EESSI. So there's commercial options from Azure and AWS as well. And EESSI in general can provide the software that's required for training. The great thing is that the attendees who come to your training events then can easily go home and set up the same software environment on whatever they have access to. So whether it's a server or whether it's another HPC system, they can use the same software stack there. The last one is the collaboration with software developers and experts. So having this central stack, it opens up all these doors, right? We get to work with developers. We get to check with them. Like if we get a dialogue going, we can check with them. You know, are we configuring this as well as we could? Is it built correctly? Does it work well? Can we verify how functional it is for all the different important use cases that you have? What about new features? Can we have tests for new features that you have so we can include them in our testing suite? And then can we evaluate? Like we also want to evaluate the performance. Can you give me some reference numbers to allow me to do that well? And then we can create the infrastructure to allow performance monitoring and to allow people to visualize, to see that performance monitoring, right? We can put that information on the web, right, through GUIs and things like that, so people can evaluate how does that change over time? Does a new feature change the performance of some aspect of this application? These kinds of things. And then ultimately, one of the nice things might be is that we get us to put a stamp on software and say this was approved by the developers, right? So that when you go into EESSI, you can say, oh, the developers of the application itself paid attention to how this is shipped in EESSI, right? So I should be able to trust exactly what's coming from here. So the other thing it potentially relieves software developers of is getting their software in the hands of their users, right? So getting it installed somewhere. They may no longer need to do things like pre-built binary packages because we're effectively doing that for them, right? And then developers can leverage, like in the CI stuff, right? They can leverage EESSI themselves to provide the dependencies. They know the environment. They know it's going to be reproducible in different places. And then we can also help them because we give them access. If they work with us, they effectively get access to all the architectures that we support, right? So if there's a problem building their application, if they're using EESSI, we can see that really early on. So they don't necessarily have access to ARM Ultra or something like that. We can run that for them. We can run that test for them and see what happens as a result, if it runs and if it's functional there. So, big question, right? Who's paying for all this, right? So maybe, hopefully, it sounds good, but who's paying for this in the end? For the last couple of years, the answer was nobody. It was a community project. People were providing resources. We got support in terms of sponsored credits from AWS, from Azure, and also there's a kind of a cloud infrastructure in Europe called Phoenix which is like the research cloud infrastructure. They also give us some resources as well. So we run on the basis of volunteer effort and then some donated cloud resources. But now we have a project, or at least part of a project called Multi-Scale. It's a Euro HPC Centre of Excellence. It's a 4-year project. It started in January this year. Has a budget of about 6 million. There's details about what that 6 million is made up of. So 50% comes from the EU, 50% comes from the national funding from the countries who are involved. Roughly 50% of the 6 million is funding for EESSI-related activities. In general, the project is a collaboration between EESSI and CECAM, who I kind of indirectly work for, has a total of 16 partners. So the EESSI is all about the technical stuff, and then the CECAM network is providing some scientific expertise. The scientific targets of multi-scale are in the multi-scale space, and those are simulations of 3 use cases. So it's the certification of helicopters for civil transport, battery applications, and then the use of ultrasound for non-invasive diagnostics as well. So they're from a broad range of scientific cases, but the idea is to show that they're all connected because they use different scales in their simulations, and then EESSI is the backbone that allows us to deliver the software that they will use within our project. And I think, yeah, that is everything, almost right on time. There's a lot of links on this slide here about various things, the paper, how you can join our Slack channel, our documentation. You've already probably seen some of our stuff on our GitHub repository, but everything we do, almost everything we do is publicly available there for you to have a look at. We have a YouTube channel. I don't know how active we are on Twitter, but it exists at least. And then we have open monthly meetings at the first Thursday of every month as well. Thanks.
Thank you so much. Any questions? It was awesome. Hey. Coming. Cool.
Hello.
Hi.
I'm not a Gentoo specialist, but the release SO version that you present there, that you presented, that information like 2021 makes some sense, so you can communicate with what exactly is the prefix that you have, or just because, oh, this day we create a prefix and we'll call that 2021 something.
So you mean inside the CVMFS directory? You mean the?
For instance, in the YAML file that you presented. Like choose the
that's to do with the software. So that's the release that they have, yeah. So OpenFOAM have a release that they call 2021 something.
Oh, it's not about the prefix.
It's nothing to do with the, no, it's to do with the software. So that's open. The other one there was 8, right? So it's OpenFOAM 8.
Okay.
There are 2 different branches. I don't know the details, right? But there are 2 different branches of OpenFOAM. And so that's basically the 2 different, I think that's the 2 different branches. And I'm not an expert. But inside that file, that's all to do with the software, right? The version of the software.
My question specifically for prefix, because there is a version, like in EESSI, there is a version for prefix that is usually a year number and something.
You mean for the compatibility layer, or
yeah,
okay, yeah. So the compatibility layer, basically we build it off of a commit, off of a hash commit in the Gentoo prefix of Gentoo prefix, right? So whenever we build it, it comes from we basically take a hash, or it's a Git repository, right? Gentoo prefix. So we say we take this hash, we're going to work with this, and then we have to make changes on top of that, right, to suit our environment a little bit. But it's on the basis of that, and so we do that at a certain point in time. Right, so it's the day that the year or month that we do that, right? So for example, the latest version, there's a new compat layer just put in place like a week or 2 ago, which is 2023.0. What was last month? 04, right? So that's the latest one, because we just did one like a couple of weeks ago. So that's the latest compat layer. So it's not like a release of Gentoo. They don't work like that, right? So then you're off of a hash at a certain point in time.